All right, simple harmonic motion and the simple pendulum. The purpose of this is to derive the time period equation for the simple pendulum. You're going to take a leap of faith on a few things with radians here. If you want more details on radians, ask me or ask a pre-calc student or ask your math teacher about why we use radians for this as opposed to regular degrees. But here we go. What you see here is a free body diagram for a simple pendulum. And let's label some of these force vectors. Here's tension force. Here is the force of gravity of the pendulum bob moving straight down. So since the force of gravity is offset by some angle theta, we can resolve that force of gravity into an x component and a y component. And I notice here that the tension force will equal and be opposite of the force of gravity in the y direction. So I can make this assertion. So those two vectors cancel each other out. I can also say that the only force that's going to be acting upon that pendulum bob is going to be the force of gravity in the x direction. And so I know force of gravity in the x direction is going to be mass times gravity. And paying a lot of attention to this right triangle here, that's going to be the same as saying the sine of this angle, because the force of gravity in the x direction is opposite. Hypotenuse is going to be right here. So I've got sine of theta. So the force acting on a simple pendulum is the gravitational force in the x direction. Now let's look at Hooke's law. Now, Hooke's law describes the motion for a mass spring system. And you might say, well, this isn't a spring. But both a spring and a pendulum exhibit simple harmonic motion, so we can kind of use the same equations. So Hooke's law says the force equals kx. And in this particular case, I'm going to flip the negative sign over to the force as opposed to the spring constant. And so I'm going to say here that my force is going to be negative mg sine theta equals kx. Let's talk about what the x is here. The x in a mass spring system will be the amount of compression or stretch in the spring. However, in a pendulum, it's going to be the length of the string on the pendulum, which is going to be this here. But there's a little bit of a catch, because that length of the pendulum is offset by some amount of degrees. And so when we describe the length of the pendulum, this can also be the length times the amount of degrees the pendulum is offset from its equilibrium point. And that's because, remember, the pendulum travels in a circle, and every single time this swings, the length of the pendulum relative to the ground gets closer and closer, so it looks like the length of the pendulum gets longer and longer. So we are going to make the x value the length of the pendulum times the angle. So, rewriting it, what I just said, let's rearrange this equation one more time to isolate the spring constant. And what you will see here is a new expression for k. And what I'm going to do with that expression for K will be on the next slide. So I've got negative mass, gravity, sine theta, all over what I had on my previous slide, divided by the length, times theta, equals my new spring constant. Here's where this radian stuff comes in. So when we are measuring angles in radians, there is an assumption we can make. We can say if the angle is going to be less than 15 degrees, the sine of theta is pretty much equal to the angle itself. So that's because the sine of the angle and the angle itself are actually measuring the chords in the circle, and those chords in the circle are pretty much the exact same size if the angle doesn't get greater than 15 degrees. You may have seen in the pendulum lab that if you increase the angle greater than 15 degrees, it was difficult to get your pendulum to work correctly. And that's because at that point in time, the angle of launch did not equal the sine of that angle, and you ended up having a disparity in that ratio. So this equation works really well for pendulums with a launch angle of 15 degrees or less. So what this means is that the angle and the sine of the angle can cancel each other out. And then I'm going to be left with this expression here. Well, let's look at the time period of a mass spring system. Again, we can use this equation because a mass spring system experiences SHM just like a pendulum. I'm going to plug in this new equation here. And remembering here that gravity is negative 9.8, I'm just going to make those negative signs go away. And then what's going to happen is I'm going to clean up this equation to say and remember when we talked about during the Kahoot that mass should have no influence on the time period of a pendulum? There's the mathematical reason why. Since it's simple harmonic motion, with respect to gravity in the x direction, and the masses cancel out here, I am left with the time period of a pendulum being equal to 2 pi times the square root of the length of the pendulum over gravity. So it's really helpful from time to time to figure out where these equations come from rather than just memorizing and knowing when to use them. Because if you know the conceptual basis behind making the equation, they become easier to understand and apply later on. So let's take a look at what this equation is. So for the time period of a pendulum, T equals 2 pi. Again, 2 pi represents 360 degrees in a circle, times the square root of the length of the pendulum, which might as well be the displacement of the pendulum bob from the ceiling, divided by gravity of negative 9.8. So hopefully that is going to enable you to answer the questions that are on page 380. 380, or excuse me, 379, numbers 1 through 4. So hopefully that works for you. Have a wonderful afternoon.